Okay, I want to say something about monodromy today. So suppose we have a variety, and we'll stick to the case of x1 to the n. Then up to picking base points, we get a map from the fundamental group of V to this pi 1. So if you think of this as the complex numbers, then this is kind of boring. But if you think of sort of an orbifold, keeping track of I and omega, then this is isomorphic to SO2 from C to the N. So we get this kind of map. And so the relevant thing to look at becomes this group H, which is, let's call this whole map. So phi to be, look at the image of phi 1V, you take its Zariski closure inside, well, it doesn't actually matter that much, but let's just work inside the real group. SO2R to the N. Okay? And the question becomes sort of what these images look like. So if two coordinates of V are isogynous, let's say n equals 2, and V equals like some happy curve. Let's just start with the, so V equals some happy curve. So V is pairs of elliptic curves which are isogynous with a cyclic isogeny of degree m. So then if m equals 1, it's not hard to see that H is just sort of SO2R embedded diagonally inside here. P1 is just a diagonal. And if m is bigger than 1, you get something very similar. You get this embedding, but now it's not diagonal embedding. It works by G goes to G in one coordinate and HG, H inverse in the other. So it's a conjugation with its little, so it's most natural to write H as M001. So it's not in SO2R, it's in GL2R. Of course you can scale it down to be in SO2R. And so you can see it's this, because in the upper half plane, if you pull back, the upper half plane squared, this curve becomes Z, comma MZ, and you can sort of see this happening explicitly. Okay, and so what we're going to prove, and this is a special and significantly easier case of a theorem of Delisle and Andre. Is that, and A is before D. I'm grade 3. Is that unless this kind of thing happens, unless the coordinates are isogynous, then your monodrome is sort of as big as can be. So, if V is irreducible, and for any pair ij in 1 to n, the projection onto the ith and jth coordinates of V x1 squared is not a Hecke curve. So it's not one of these TMs. Then H actually all SO2 R to the n. Sorry, I guess it actually equals the way I defined it. Okay, so we'll prove something similar in the GN case, and I think maybe the Diophantine case, I don't remember. It gets a bit harder here. But this is still a relatively easy case of the theorem. Okay, so first I want to show that it's sufficient. So you see what's happening for n equals 2. So this is one of the ways in which this sort of structure of x1 to the n is simpler than gm to the n. I think I mentioned before, in sort of, if you're in a torus, you can have relations between all the coefficients at once in arbitrary linear combinations, which really involve all the coordinates, whereas in x1 to the n, all you can do is pick two coordinates and do stuff to them. So somehow, that's simplification. Okay, so we need two lemmas to establish this. So first of all, if you have a subgroup H, that's to R to the n, and for all ij, the projection of H is SO2R squared then H is just SO2R to the n. Okay. This isn't hard, you can show it in many ways. The sort of the key input, I'm not going to go to the proof. The key input for this lemma and many lemmas like it is something called Groussat's lemma. And it says that if H is in G1 cross G2, where G1 and G2 are simple, and natural projections are surjections, then either H is equal to all of it, all of G1 cross G2, or G1 is isomorphic to G2, and H is equal to the graph of an isomorphism. Okay, so SO2R is not quite simple, but it's close enough that you can apply this lemma over and over again, sort of keep building up H. Okay, so that's one of the two things we need to reduce to n equals 2. How's the reduction go? The reduction will go, we're going to take V, we're going to project it down to x1 squared. We're going to argue that fundamental group downstairs is a projection of H, but we got to show that it's actually true. So the other lemma is very general. So if V1 and V2 are algebraic varieties, and V1 onto V2 is surjective, the map of fundamental groups is essentially surjective. So then phi of pi 1v. So again, to make this well defined, I got to pick base points, but none of the things that I'm saying can depend on the choice of base points. Pi 1v1 inside pi 1v2 is a finite index. Okay, so if we have this lemma together with this lemma, then the n equals 2 case is efficient, because we can project, heuristic close something of finite index to get something of finite index inside here. There's nothing of finite index out of r squared, just the whole group. Sketch. So it's not very sort of hard to see what happens. The point is that if phi has connected fibers, then this basically actually equals pi 1v2. It's surjective. So all you're going to do to show this is you have to know that paths here lift to paths here, right? And that's followed by this with some rational section. So this is sort of algebraic nonsense. In general, you have an action of pi 1 v2 acts on the connected components of the pre-image of some base point. And the kernel of this action and the phi, the image of phi is equal to the kernel of this action. So you can lift the path, you can make the different component, but if you do it a few times, you get the same one, and then you can just join up again. That'll give you a lift in your path. And these are proofs, but with some basics, the big proofs. Okay, so n equals 2 is really the main case of this lemma. Okay, so now suppose you have a v inside x1 squared is a curve. Oh, I guess, sorry, there is no theorem, you have to assume v is not a fiber as well. It has to project dominantly onto every coordinate. Otherwise, you get nothing with that coordinate. So it's a curve, and it's not a fiber in either direction. Okay, then V surjects onto both projections, and so pi 1v mapping onto S to Z. So both projections, Pi and P1 and P2, has finite index. I being 1 or 2. And so then H, image by 1V is zeroistically closed. Inside here, surjects onto L2R. Under either P1 or P2. Okay, so that tells us that essentially, this isn't quite right as a center, but it's close enough, that H is equal to G to the set of these guys. Okay, so it's some graph of an isomorphism between S2R this, or we win. So, or H is all of S2R squared. So assume the first thing for contradiction, or to see what happens. Okay, well now what could this H be? It can't just be an arbitrary real guy, it has to preserve some integrality structure as well. Right, so we know that if you look at H and you intersect it with SL2Z squared, in particular you recover the actual image of by 1V, and in fact not just Zariski closure, but this guy itself surjects onto SO2Z. In either coordinate up to finite index. So this thing surjects onto SO2Z under projection, which means that this conjugation by H has to essentially preserve integrality. So at the very least, it follows from this very quickly, just write linear equations for what it means. It means that, I mean, it's stronger than this, but essentially equivalent. That if you conjugate SL2Q elements, you have to get back to SL2Q elements.
Okay.
Okay, so now let's see what this means for H. So this will turn out to imply that H essentially has rational coefficients. Essentially, it doesn't actually imply that though, because for example, for the M001 matrix we had, if you put it down in SL2, it's going to become root M001 over root M, and you actually can't make that happen. I don't know, it doesn't have rational coefficients, and it preserves this. But that's sort of the only thing that can happen. So pick, to sort of make this argument formal, what you do is you pick a sigma inside the automorphism group of C over Q. And so in applying sigma, you see that for gamma in SL2Q, H gamma H inverse is equal to sigma H gamma sigma of H inverse. Just applying sigma to the entire relation. which means that sigma of H inverse H is the stabilizer, the centralizer, I guess is the word for it, centralizer of S of the Q. S of the Q is a risky dense, S of the R, and so this is just plus or minus 1. And so you get a map from this automorphism group to plus or minus 1. And so we have two cases. Under this map, this map is trivial. So we get, let me write, I guess where it is. So we get a map C from this to Z mod 2. The first case is that C is trivial, which means H is equal to sigma H for all the automorphism guys, and therefore H is in S of the Q, and therefore we're done. H of the Q, Z, and HZ always have an isogeny between them to some degree. I'm just changing sort of coordinates in your lattice. And the second case is C is non-trivial, so H is defined over some quadratic extension. And the elements of H are purely imaginary. So i.e. K is equal to Q root D, and H is root D times H prime, where H prime, well, it's not going to be in S of 2Q now, but it's going to be just in M 2Q. So, or maybe it's better to write G of 2Q. Okay, and now we're done once again, because acting by an element of G of 2Q also gives you a fixed isogeny. Okay, so these are the possible H's that show up. Okay, the H's are correct, and so all that's left to check is that the only variety is giving you these fundamental groups. These images are the Hare curves themselves. So suppose the image of phi of pi 1v the risky closed is equal to this H, so which is this G H G H inverse. Okay, so now consider G0 be a connect component of the inverse image of V in the upper half plane squared, such that V0 is stabilized under this guy here, so under H. Intersect SO2Z squared. Um, One second. So I may have messed up here. Everything's as far as right. What we want to conclude now is that V naught is actually stabilized under all of H. It made sense yesterday. So give me another minute. Then if it doesn't make sense, I'll get back to it later. Alright, so I guess magic, which I'll remember for next class. So, some trick which I believe is simple, but I can't remember at the moment. With definability, gives you that V naught is actually stable under all of H. Yeah. Alright, so once you have this, it's not hard to finish. So the real dimension of H is 3, whereas V naught is real dimension 2, so the atom has to have a one-dimensional stabilizer. So H acting on V naught has a one-dimensional stabilizer. Which means that if the point I, Z, or let's say I, Z naught, is in V naught, then the stabilizer of I in the first coordinate is just SO2, and so the stabilizer, so you must have that H, SO2R, H inverse stabilizes Z naught. That only happens if Z naught is equal to H times I, which only happens if V naught is the variety Z, HZ. Once you have a single point, just act with H and you get all of this. Okay, and this is a mapped down later. Okay, so modulo this magic step. Let me show you guys. That finishes the proof. And so in the general case, which I won't say anything else about, we have a similar lemma as this whole thing, where in the, if you look at the image, the monodromy group of any subvariety, of a Shimura variety, is the risky dense in the entire thing, unless you contain inside some mutually special. I don't know any proof of this which doesn't use some fairly serious Hodge theory. And to be honest, I don't really know that proof either. So we won't be covering that proof. It seems likely there's a proof with homonormality. You can sort of get started and do quite a bit, but no one's worked on the details. I think that would be quite interesting. But at the moment, the only proof is using the linear machinery with Hodge theory in the general case. All right, so let's sort of, I want to get back to X Lindemann. And show how this kind of lemma is relevant. So recall the setup is we have a variety V in x1 to the n, and an algebraic variety, well, W in h to the n. These are both algebraic, and W is a preimage of V. So then by this theorem over here, by previous theorem, we're going to assume that the monodromy group of V is as big as it can be. Because if it's not as big as it can be, it's contained two coordinates are isogenous, and you can basically get rid of that coordinate. It basically means you're living inside a smaller power of the modular curve, up to a level which doesn't really matter. So we're going to assume this kind of thing. All right, so last time what we showed using our volume estimates is that W passes through polynomially many fundamental domains upstairs. And so if we once again define I with the set of elements in SL to R to the n, such that gamma W intersect a fundamental domain is contained inside parameters V into the fundamental domain. So we showed using volume estimates. By the way, this sort of argument was done by Yasa Evan Umo, first of all. They introduced this volume argument. But we showed that sort of the curve inside W, it has a lot of volume and a small radius, and inside the fundamental domain it has bounded volume, which means it has to pass through many fundamental domains. So we showed that this n of I z t is goes at least as fast as some power of t. And if you're interested in the general Shimura variety case, that argument works basically verbatim once you make all the right definitions. Okay, so now using Pila-Wilkie, like we did for the GN case, we can get a holomorphic curve C in essence of C to the n with C in sort of the natural complexification of I. So we first get something in SL2 R to the n that we complexify like I did before, to get this polymorphic curve C. Okay, so then we run through the argument as before, and then we mean it for the GM case. So the first case is that C doesn't stabilize W, and in this case, you sort of replace W by C times W, and now the dimension is one bigger, and so you can proceed the induction that way. The second case is that C stabilizes W. Let's say that W is always a group. In other words, you can get an algebraic group G, and in fact you can make it defined over Q, because you have many Q points in I to start with. Which stabilizes W. Then if G doesn't stabilize V, or rather the primitive V, so maybe we can say it, then we pick some element inside the rational points of G which doesn't stabilize V, and we send V, we replace V by the intersection. So pi of pi inverse V intersect G pi inverse V. And that makes the dimension of V go down. So again, we get a smaller counterexample. So by doing both of these steps finitely many times, we get to a case where W is stabilized by something, and the preimage V is stabilized by the same thing. Is this sort of clear? These are the same steps we did in the GM case. So yeah, this is the first part where we're going to solve it now. But it's the first part where you sort of the monodromy becomes substantially an issue, because in the GM case, once you have a G stabilizing your guy, you can just change coordinates and you can make it be translations in the first coordinates, and that sort of lets you get rid of a variable. You obviously can't do that over here because there are genuinely different subgroups inside S2R and the end. The diagonal S2R looks very different than a coordinate S2R. Okay, nonetheless, what you can do is you can let gamma be the stabilizer of our component of V naught. So V naught in pi inverse V is the component which contains W, And we can just define gamma to be everything which stabilizes it. And so we know, what do we know about gamma? Well, we know that G, a positive dimensional group, is contained inside gamma. We also know that phi of pi 1v is contained inside gamma. Okay, this doesn't require anything fancy that we've done. This happens at the very beginning. Okay, so now let G in SL to R to the n be the Lie algebra of gamma. So a priori it could be finite, but it contains G, so it contains at least some polydimensional thing. So dimension G bigger than 0. And how we're going to use this guy? Well, G is stable under conjugation by anything in gamma, so in particular, under conjugation by this guy. Alright, it's a group, so certainly conjugation checks the Lie algebra. And so therefore, G is stable under conjugation by the heuristic closure of this guy, because the action of conjugation to the algebra is algebraic. And what is this guy? This guy is all of SO2R to the n by assumption. Okay, now there's very few normal subgroups that start at the end. There's very few subspaces in the Lie algebra which are fixed and start at the end. So in particular, we get that G is equal to SO2R to the I for some non-empty I inside here. In other words, some coordinates are 0, and everywhere else you have sort of free range. These are the only unstable subgroups. Release of algebras. Okay, so then O log 1 is an I, which means that SO2R across a bunch of points, so that SO2R in the first coordinate stabilizes V naught, which means that V naught is equal to the upper half plane across something else, V1 or whatever, which just means that V is x1 across some other algebraic variety, let's say V2. Because you can freely act on the first coordinate. Okay, and so now you can, and in the GM case, you can project to x1 to n minus 1 and use induction. That's the other thing. You don't need induction. You can just project away all the I coordinates and then see what happens there. It's a fast way to finish. Okay, with this trick of sort of, you get some positive dimensional guy, and that's not so useful because you have these sort of weird subgroups now which don't really give you very much. But then you use the actual monochromy to upgrade from that to some genuine sort of normal guy, and the normal guys give you a decomposition, which is what you want. Right, any questions? Okay, next time I'll finish that magic part and then we'll move on.